So now we need to address that question of what might cause a limit to fail to exist. When can a limit fail to exist? Well, the good news is that there's a few different cases that we can look at to determine what might have happened. All right, so the first case is the left and right limits don't agree. So we just said that basically that if a limit's going to exist and equal some value, then you need both one-sided limits to exist and be equal. Well, they could possibly both exist, but be different values. So let's take a look. This is a classic example. If we look at the limit as x approaches 0 of absolute value of x over x. Okay, so realize that, think about this function, absolute value of x over x. We would have to really define this piecewise because of the absolute value. So the absolute value of x over x is equal to 1 if x is greater than 0, because the absolute value wouldn't really matter and the x's would then cancel. Or it's equal to -1 if x is less than 0, because the absolute value would make the numerator positive, but the denominator would still be negative. They'd have the same quantity value, but they would cancel with a -1. And obviously x can't be 0 because you would have a 0 in the denominator. So what does this function look like? So what it looks like is basically for any positive x, you're always at 1. All right. But you don't have a value at 0. And for any negative, you're at -1. And you still don't have a value at 0. So that's what this function looks like. It's always 1 for all positive numbers and always -1 for all negative numbers and not defined at 0. So let's look at what happens. So obviously, let's break it down into the side limits. The limit as x approaches 0 from the right of absolute value of x over x. So as you approach from the right, you appear to be heading towards the value 1. But as you approach from the left, you appear to be headed towards the value -1. So these both exist, but the problem is they are not equal. They don't agree. So we would say this limit as x approaches 0 of absolute value of x over x, and we often write DNE as an abbreviation for does not exist. Okay, so there's one reason why the limit might not exist. The left and the right, even though they both exist individually, don't agree. All right. What's another reason that the limit might not exist? Well, you can have unbounded behavior. Let's talk about 1 over x squared. So 1 over x squared looks something like this. Okay. So what's happening is, as we approach, say, let's look from the right, as we approach 0 from the right, our values go up and go off to infinity, right? Similarly, as we approach from the left, approach 0 from the left, our values go up to infinity. Okay, so infinity doesn't count as a valid limit because we need it to go to a real number, and infinity itself is not a real number. It's a place you're headed to. It's a concept of where you're headed. So in fact, neither one of these individual limits exist because they both go to infinity, which doesn't work. So this is the unbounded behavior here. And we would say, two different things. We would say this limit does not exist, okay? But because of the nature of how it doesn't exist, we would say or write the limit as x approaches 0 of 1 over x squared equals infinity. But we realize that this means it does not exist. So if there's a case where the limit doesn't exist and we can say, and we can show, in a way of writing it, that what it does to not exist, we do that. So that's why in this case, we would usually not write that. We would write equals to infinity, understanding that we actually mean it does not exist. All right, but we're able to say, because both of these are going to positive infinity. Now, if they're going to different infinities, we couldn't write that. So we'll see examples like that. So the idea is, if somebody gave you only two choices and said, does this limit exist or not, you would say not. But if somebody asked you to write what this limit is, you would normally write infinity, even though you're not saying the limit exists. You're just clarifying how it doesn't exist. Okay. The third case is kind of weird. So I'm giving it the name strange oscillating behavior. And this is the classic example, is sine 1 over x. Okay, so let me give you an idea of what this looks like. It's not going to be a great drawing, but I have to do the best I can here. So sine 1 over x is very strange, because what happens is it ends up, so if you're coming from the right, it's like this sine curve, but as you approach, it gets tighter and tighter and tighter, and it goes up and down infinitely as you approach 0. It's still between 1 and -1, but it keeps going up and down in there infinitely. And the same thing, similar thing from the left. So these should be all the way between -1 and 1, but you get the idea. All right, so the thing is that since this keeps going up and down infinitely as you go to 0, it doesn't actually go to any one number. It seems to be headed to all the numbers between -1 and 1, and not one in particular, because as close as you get to 0, the function takes every value between -1 and 1, and even if you get closer and closer, it still takes every value. It doesn't actually approach any one value. So for that reason, this limit does not exist, okay, because it doesn't head to one real number. That's a very particular case. This is not something you run into a lot. The first two cases are quite common, but you should know that this is a case where the limit does not exist.